Hello, this is video number 65, and in this video I want us to look at another sorting algorithm. ALG for short. We're on a first name basis. And you immediately think, and I can feel the thoughts, why do we need another sorting algorithm? We already got bubble sort. It's perfect. We couldn't improve upon that even. Well, maybe we could. Part of why we are even interested in computer science theory, and specifically in algorithm analysis, is so that we can make wise choices about whether or not one algorithm might be better than another algorithm in certain situations, like if we're sorting thousands of data items or millions rather than just a few. And sometimes it does pay off for us to do a little bit of time, do a little bit of homework, and contrast and compare. And I'll shut up and start writing. The one I want us to look at, the other sorting algorithm, is merge sort. M-E-R-G-E. That's a horrible M. Merge sort. And the big idea, you remember the big idea behind bubble sort was, well, let's just go through the whole list. We'll swap pairs that are out of order, do that over and over again until they're in order. There. Bubble sort in a nutshell. Bubble sort in a nutshell. The idea of merge sort is very different. Split the list in half. We never did that in bubble sort. Split the list in half, sort each half separately, and then merge the two sorted halves back together. Thus the name. There, a short and sweet summary of what merge sort's going to do. What it will do is split the list in half, sort each half separately, and then merge those two sorted halves back together. How simple is that? Kind of feels like there's something missing though, doesn't there? Split the list in half, yeah, that should be fairly straightforward. But this piece, sort each half separately, I mean, how are we going to sort each half separately? This is the sorting algorithm. This one was supposed to do that. Oh yeah, footnote here. Little star, asterisk. Sort each half separately using merge sort. Yikes. Merge sort is a weird kind of algorithm called a recursive algorithm. Definition. A recursive, R-E-C-U-R-S-I-V-E. A recursive algorithm, abbreviated again, that's ALG, is an algorithm that is defined in terms of itself. There. And that definition might not put you any closer to a comfort zone than the original description did. But so let's look and see here. Merge sort. Split the list in half. Sort each half separately. How are we going to do that sort? Oh, we do that using merge sort. We're specifying this algorithm in terms of itself. It's almost like it doubles back on itself. So now we'll have a list that's half the size. And we start merge sort again. How is merge sort going to split that? I'm going to sort that half a list. It's going to take that half a list and split that in half. And here's the weird thing. Yada, 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 split, 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 split. Eventually we'll be down to where there's not really anything to put in order. We're down to a single element of the list, and that's got to be in order. There's no way a list of size 1 can be out of order. And if that sounds confusing, that's because it is. Recursion is kind of a tough concept to get a hold of, but we will. Trout, no! Michael! Pardon the pack, please. Well, I get rid of that, partly because it's scary, but primarily because it's taken up board space that I really, really need. I think it's a lot easier to talk about merge sort and even recursive examples and recursive algorithms in general, just to look at an example. So here we go. Here's a list of numbers: 26, 16, 5, 15, 20, 9, 24, and 14. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, I think I've got it. So that's my entire list. I'll even put a bracket under it to make it official. How does merge sort that list? It doesn't go through pairs at a time. No. That's the olden days. That's bubble sort. It splits the list in half, and this one's easy to split in half. Come this direction, we'll have this half. 26, 16, 5, 15. Go this direction. This is the left, by the way. I'll put an L for left. Over here, this will be 20, 9, 24, 14, also known as half to the right. And I will give them their very own brackets to show that from the point of view of the algorithm, this will now be a complete list, except it's now a complete list of size 4 to put in order. That's blue. I hope it shows up as blue in the video, but who knows. And this will also be blue. They're both at the same level of recursion, is what we would say. Oh, I hope I didn't just unplug my microphone. I guess I'll find out. Well, here we go anyway. This is the left half, that's the right half. Now, here's the greatest trick. People that have made it through several computer science classes will tell you one of the biggest tricks that you really have to work to get used to is putting the blinders on when you're working with recursive algorithms. You have to forget that the algorithm is recursive and act like this is the whole shebang. This is the whole story. Watch what I'm talking about. Now we've got to sort each half using merge sort, which means we start all over again with this as the only list that merge sort has to put in order. What does merge sort do when I give it this list and say, put that list of size 4 in order? Well, let's see. It's got to be a stepwise sequence. The first step says, split the list in half. Look what happens. This gets split in half. 26, 16 is the smaller left half over here. L for left. 5, 15, whoops, did I put that? No, that's right. This L goes up here. Put it close to the tray. Put the R close to the tray. There, clean up my picture a little bit. I'm confusing myself. 5, 15, that's not difficult to do. Confuse myself, that is. The right half. And I'll use a different color. We're at a different layer of recursion. Pause and reflect already. What's happened? Somebody said, please put this list in order using merge sort. And merge sort says, okay, we'll do. The first thing I'm going to do, though, is split the thing in half. I don't want to have to sort that whole thing. I want to do it half at a time. So it splits it in half, 2 halves. And we present this blue tray here. Actually, the algorithm presents it to itself. It says, okay, now look at this blue tray. Put that in order using merge sort. It says, yeah, you know what? The first thing I'm going to do is split that list in half. And that's where we are now. It just now split that list in half. What it's going to do is, it's going to tell itself, it's talking to itself. Put these 2 lists in order using merge sort. Put each half in order using merge sort. So now we narrow down our blinders, we get our focus even more focused, and this is the list that merge sort is now charged with sorting. Surprise, guess what it does? The first thing it does when we get a list 2 is, it's got to split the list in half. We're almost done splitting. Here's 26 by itself, half the list. 16 by itself, half the list. And yet a different color. A tiny little list of size 1 is 26 all by itself. A tiny little list of size 1, 16 all by itself. with a tiny little L and R just for them. L and R. You know what? We can't split that any further. We're not going to split this into a 2 and a 6. It's just a single number, a single 26. This is a single 16. No splitting into 1 and 6. We can't split any further. So let's see. According to the algorithm, split and then merge the two sorted halves back together. So we've reached the bottom outline down here. This dotted line says you can split no further. That's as far as you can go. So now we're going to have to merge. What do we merge? We merge the left half and the right half back into a tray of size 2, which will be a red tray. All my red trays will be a size 2 if I remember. Let's see. So here we go, the left and the right. Well, I'm putting this in increasing order. So 16, since that's less than 26, it gets to jump down in this red tray first. There. Now we have completely used up all of the little green list over here, so there's nothing left to do but to copy down the 26. Now voila, as if by magic, pretend. We do a lot of pretending with recursive algorithms. Pretend that is the complete list, 26 and 16. Then our job is done. We just now merge sorted the 16 and the 26. We split the list in half and we merged them back together. So this is a tiny little microscopic version of the entire merge sort. Take the list, split it in half, merge it back together. And you merge it like a zipper zips up. You take the smallest one, then the next one, then the next one, and so forth. Now this one, meanwhile back at the ranch, when we told merge sort to merge this half up, no we didn't. When we said merge sort this half over here, it says yes, we shall do that. I'm going to split that into two tiny lists, one of size 5, one of size 15. Left and right. I'm going to quit writing the L and R's. I think those are confusing things. Clearly, that's what professors say when they don't really have a good explanation. Clearly, this is the left half, that's the right half. There's no ambiguity there. So now I'm ready to merge this little microcosm piece of merge sort. Here's a list of size 2, split it in half, merge it back together into a list of size 2 again. Back where we belong. Where do we belong? Well, 5 is less than 15, so 5 gets to get in the red tray first. And again, we don't have any numbers to compare over here because we've already used up the 5, it's gone. The 15, we can just copy that down without looking. What have we done? We have done two tiny little microscopic versions of merge sort. Take a list, split it in half, merge it back together. Take a list, split it in half, merge it back together. Since I'm not writing L and R, I can at least write merge. Where are we in the grand scheme of things? Well, we're back to blue land now. Look at this. Well, we're ready for a blue tray, which can hold 4 numbers. Why so? The last time we saw the blue tray, it had just been presented to merge sort. And merge sort says, you know what, before I do anything else, we like merge sort, don't we? It's actually a procrastinator's dream. It doesn't do any work until it absolutely has to. Splits and splits and splits and splits. We don't do any comparisons until we reach rock bottom down here. Then we can't put it off anymore. To do the merge, we've got to do some comparisons, and away we go. This time it'll be a little non-trivial, perhaps. But now we've sorted the red left half and the red right half. We're ready to merge those back into a blue list of length 4. Here we go. Look at this. We look at the first one. We know, this is an important point. By the time we get to this point, we know the little miniature red list over here is in order. We know the little red list over here is in order. How do we know that? Well, because we just got through merge sorting them. They were the bottom, the base cases of merge sort. We get down to a single element, we merge it into a list of length 2 that is definitely in order. Otherwise, we haven't written our code correctly. On the right-hand side, this little red tray, that is definitely in order if we did merge sort correctly, because we merged these two together and put them in order as we were putting them in the red tray. Now, as we put things into the blue tray, we not only need to make sure they're in order, but here's a freebie. We get to assume that this red tray is in order, that red tray is in order. So all I got to do to figure out what is the first number in the blue tray is to look at these 2 numbers right here. This is the smallest one in the second tray. This is the smallest one in the first tray. 5 beats 16, so 5 gets to go in first. Now I've used up the 5. I'll move my little finger pointer here to the next number. Now I compare 15 and 16. Who wins that comparison? Well, 15 does. 15 is less than 16. So 15 gets to jump in the tray next. This is the merge step here. This is the comparisons, where the comparisons start showing up. Now then, since I've got all of that red tray taken care of, then I can just copy this one down without looking anymore. There's not anything to compare it to over there anymore because both those numbers are already in the blue tray. So here we go. I just copied down the 16. I just copied down the 26. Bada boom, bada bing. I got a list of length 4 that was in order. And if I'd started my example right here, that would be the complete merge sort. Split it in half until you can split it in half, no more. Then, when you get down to the bottom, there's nothing splittable anymore. You start merging these tiny little lists together. And the list gets larger and larger and larger as you come back out of the hole. This is digging a deeper and deeper hole, splitting and splitting and splitting till we get to the dotted line. Then we start merging stuff back together, and that's how we got to this blue tray. Now let me see if I can do this a little bit less verbosely. I got to find this is the black marker. This gets split left and right. You can say it along with me now. Well, I need a red. I need 2 red trays. If I'm going to merge sort that blue tray, then the first thing it does is split it in half. Split it in half. On this side I've got 20 and 9. Over here I've got 24 and 14. Now then, merge sort, keep going. Now you've got to sort the left half and the right half of this little split. The left half, when I merge sort this red tray, the very first thing merge sort does is split it. 2 lists, 20 and 9. Those go in little green trays. There's nothing special about the colors, just I wanted to distinguish what's going on at the different sizes of lists. All the red lists are length 2, all the blue ones are length 4, all the black ones are length 8, there's only one, and the little green ones are length 1. So this one, when this gets split into 2 lists, there'll be 24 on the left, 14 on the right. 24, 14, and those are all little green lists. Now actually I should probably draw a dotted line here. These 2 lists are that one split in 2, those 2 lists are that one split in 2, and those 2 red ones, that's the blue list split in 2. There, merge time. Merge them back together. When I merge these 2 back together, they're going to turn into a little red list of length 2. I should just leave all of these markers open. Why can't I remember to do that? I'm going to need 2 red trays. Okay, merge these 2 back together. Here we go. What about the 20 and the 9? Well, 9 is less than 20, so 9 gets to go in first. And already I've completely used up that little list, so 20 gets copied down without a care in the world, without any further thought. And that was a merge. Here is a merge. Who is smaller, 14 or 24? The 14 is. And the 24 I can copy down without any further thought. So now, merge sort has sorted this little tiny pair of lists into a single red list. Same thing going on over here. Now what? Now we're ready for a blue list. Now that I've got the left-hand side and the right-hand side of the blue done, I'm ready to have the final sorted version of the blue list already and in order. It gets a little more complicated. Let's see, 9 and 14, the 9 wins that one. Now I've used the 9. The next number to look at over here on the left is the 20. What about 20 and 14? Well, 14 wins that one. So now it's a tie. This one won with the 9, that one won with the 14. Now I compare 20 and 24. 20 wins that one, and 24 gets copied down without a second thought. Where are we now? Well, merge sort has sorted this blue list into a sorted blue list. Merge sort also, meanwhile back at the ranch, sorted this blue list into a sorted blue list. Now we have 2 sorted blue lists. Where did they come from? Those were the halves of the original list, way up here in the sky. Those get sorted in our grand finale down here in our list of all numbers. I'll write merge one more time here. Merge this left-hand side with this right-hand side. I didn't label those all along because the board was getting complicated enough as it was. But here we get to see a little more clearly, I hope, what's going on in the merge step. Because with tiny little lists, it's kind of hard to see. Where my fingers are on the board is very important, so I hope I don't mess that up. 5 and 9. We only have to look at the first two numbers. The first number in this list, the first number in that list. Why? Why? Why don't we need to look through all the numbers? Because these have already been sorted by merge sort. Whatever the smallest number on the left-hand side is going to be first. Whatever the smallest number on the right-hand side is going to be first. So we're figuring out who is the smallest number overall. We only have to look at the first number in each half. I've said that several times. I'm going to quit saying it. 5 and 9, 5 wins. Now watch the fingers here. We've used up the 5, so I'm going to increment where my finger is over here. Now look what's going on. I've got to compare the 15 and the 9. 9 wins that one. Since 9 won, I move to the next number over here. What about 14 and 15? 14 is less than 15, so the 14 gets copied down to the big list. Next, bump up the finger position over here. Now I'm comparing 15 and 20. 15 is less than 20, so 15 gets copied down, and I finally get to move the left-hand finger, for crying out loud. Over here, now we're comparing 16 and 20. 16, left-hand side zooms ahead. 16 is less than 20, so now I move the finger up here. 20 and 26 is what I compare it. Actually, 26 to 20. 20 wins that one. Bump up the finger. 24 and 26. 24 is less than 26, so 24 goes in next. That's it. That's all the right-hand side list. We still got a number left over here. Now, in this case, we only had one number. If that last number over there had been a 14, I might have had 3 numbers to copy down. It's hard to get all the possible things that could happen in a big sorting algorithm like this without huge amounts of data. But we ended up with only one number left over. There's nobody to compare the 26 to because we've already used up all those. So 26 gets copied down without any further thought. What did we just do? What we did just now on that step was assume that the blue list on the left was already in order. Assume the blue list on the right was already in order. And then we merged those together. Like here you really see the zipper effect. Pick one from here, one from there, and keep going, keep going. Always take the smaller one and then increment where your finger points on the bigger list. And if you do that, merging this together, one number at a time, you end up with a sorted list. At no point did we go through and compare pairs of numbers or anything. What we did was split and split and split and split and split until we could split no further. Then we start folding them back in together. We start zipping them together into sorted lists. It's an important point that at each step doing the merge, we do get to assume the two lists that we're merging were already in order. Otherwise, we don't get to do just looking at the first two numbers and then look at the next number. We don't get to do that. So we have to know that this one's in order. And oh, how can we know that? Well, because we told merge sort to do it. We started off by saying, here you go, merge sort this blue half and that blue half. And merge says, okay, we'll do that. To merge sort this, I'm going to split you in half first. Now it's got to put the red lists in order. Those have to be in order before we can merge those into a blue. And to put those in order, we split them and split them and split them and split them. That's what I mean by it's a procrastinating algorithm. It doesn't do any comparison and merging until after the dotted line. That's where all the work happens. That's where all the magic happens. And that is quite an example. You might even want to review this during your leisure time to understand it a little better. And until then, I'll see you online.